Uh, if you could just
Yes, sir. Yes, sir. It is visible and is also audible, sir.
okay, thank you. So as I was telling, thank you for a nice introduction. First of all, I'm thankful to Professor Srihanshu Pal and Professor Dinda for the invitation. So today I'm going to talk about information entropy based materials design. So first of all, as the title suggests, we are going to talk about information entropy. In generally, information entropy as a concept is defined in information technology and computer sciences, and how can we use it to design some interesting class of materials. So that is what is our aim. So what I'm going to talk about, of course, I'm going to not only talk about a materials design, but a interesting paradigm of material design called inverse material design. So I'm going to introduce you with that. Then I'm going to talk about a class of material called high entropy alloys. Uh, then I will get into what are the challenges in designing such class of alloys. And once we have understood that, I will talk about entropy as a design parameter. But there are obviously challenges with entropy as a design parameter. So I'll define something called information entropy as a proxy design parameter. And after that, I will talk about first open source software which we have made in our group, which is called GAS. It is called Genetic Algorithm Based Atomistic Sampling Protocol for atomistic sampling in high entropy alloys. Then we will talk about how whether we can use this entropy parameter for order disorder transition. At least phase stability, order disorder phase stability, I'll come emphasize on, and then we'll get into ordering in high entropy materials, which is a very important topic of interest with OPERA approach. Again, another open source system which we have developed, which we call order parameter engineering for random systems. And then I will basically extend it to basically strength predictions. So that is the overview of my talk. So if you feel like anywhere between my talk, if you have any question, you can just stop me because we have a lot of time. And in between there will be some stops. So I will stop there in between my talk also, and I'll expect if you can ask some questions there on the topics. So, what is inverse material design? So, in our undergraduate first year, second year, we have learned that this materials tetrahedron. So, in materials tetrahedron, the corners, we have four corners, and in those four corners, we have a structure, property, composition, and performance. So, we are taught in our undergraduate that these are the important parameters which are associated with any materials, any particular material. So any particular material have got certain composition. Its composition decides its structure, and structure decides its property, and property influences the performance. Now, when we talk of the structure, again, there are a lot of details there. So structure at what scale? So if you talk in context of say atomistic, say at a electronic scale, so you have an electronic structure, you can have at atomic scale, you have atomistic structure, you can talk about something happening at a microstructural scale where particularly in metallurgy, a lot of people are interested in, which is called microstructure. But all these are related because electronic structure influences the atomistic structure, and that ultimately influences the microstructure of the material. But what has been the tradition basically is that if this particular graph is presented a lot, and I would like you guys to basically concentrate on the right hand side. So we have certain material, we process it, and that gives us certain microstructure, and that particular microstructure decides the property, and that is the performance. So this is something which is called the deductive approach. So let me see if I can find some pointer. Yeah, I hope you can see my pointer. If someone can tell me. Okay,
Yes,
I
sir.
hope you. Yeah, yeah. So this is something called deductive approach. So it's much more an empirical approach. You take a material, you process it, you'll get a microstructure, It will have certain property and it will influence the performance. And this particular deductive or forward approach is relying upon the cause effect relations. Okay, so what cause and what effect? This is how we have been doing material science for a long time, and it is sometimes also called hit and trial approach, which we use. So we design something, of course, with some prior knowledge, but this approach can be slightly tricky because now we are talking about entirely different inverse approach or inductive approach. So suppose if I ask a question, I want a material for a particular performance, say in an aircraft or in a nuclear reactor. I know what kind of a property a particular material performance a particular material need to exhibit, and I can translate it into the property, and with some understanding I can know what is going to be what should be the microstructure and what should be the processing, and even going beyond that what's going to be the composition of that particular material. And this inductive approach is goal driven approach, and this is what we mean by the inverse approach of material design. And this is something which is picking up nowadays, and particularly computational approaches falls right into right place for dealing with these kind of material design problems, where we start with given performance, we translate it into properties, and then we go on and design particular material. So this is something which will be in the background of whatever I discuss through computational approach, or even nowadays with the experimental approach. The aim is to design, go for inverse material design, because we should be very we and as you will see later in few of my slides, that the class of material I'm going to talk about, the hit and trial empirical forward approach is not going to work. And I hope I'll be able to convince you in upcoming few slides. So, as I mentioned, I'm going to talk about a special class of material, which are called high entropy alloys. Of course, it has got, if you follow the publications which are going around, this is one of the very exciting area of metallurgical research, which was discovered in 2004 by Ye and Cantor concurrently. So, but sometimes people call them complex concentrated alloys. Sometimes people call them multi-principal elements alloy. So there are various names, and there's a lot of debate what it should be called. But let's, for the sake of simplicity, call them high entropy alloys. So what these alloys generally can have 4 to 5 elements, and they exhibit simple crystal structure. So that was the initial definition which was given for these class of alloys. Of course, it has been extended to in many directions. But for if someone who is just looking at the and listening about this for the first time, this is what we mean, that you can have a multiple number of elements, and they mix together and they form solid solutions. So as you know, if you mix at least for metallic elements, if you mix two metallic elements, few of the cases are possible. So either it can form solid solution, or it can go on and form intermetallic systems, or it just doesn't mix with each other, called immiscible systems. So these three possibilities are present. For multiple component cases, some other interesting things can also happen, that some you might form quasicrystals, or in certain cases also you go on and form amorphous alloys or amorphous material, even with metallic systems. And that was the idea when people were looking into it, that if you mix many elements together, you will be able to form amorphous systems very easily. That was the idea which was propagated earlier, but somehow people stumbled upon these kind of systems, where they started to form single phase solid solutions. So initial idea which was given, if you have a equiatomic composition, if so all elements are in equal composition. So in that kind of a scenario, the configurational entropy is maximized, so that we know from our second year thermodynamics. And as you increase the number of component, basically this n, capital N, increases, so the configurational entropy basically increases. So that was the initial hypothesis about the solid solution stabilization in these kind of systems, which was given by A. And the idea was very simple, that we know that the Gibbs-free energy change delta G is written as delta H minus T delta S. Delta H we know is the enthalpy change associated with the mixing. T is the temperature, and delta S is the entropy. Initially, when hypothesis was given, they mentioned that this delta S is basically increasing significantly as the number of component in the system increases. This is how delta G is going to negative when we have large number of elements. And this is how the entropic stabilization is taking place. But just by looking at this expression, of course, this was initial hypothesis and it has been challenged recently. Delta S doesn't, at least looking over here, it doesn't depend upon the chemical identity of the elements. So I can mix any elements in greater number and they should form solid phase solid solution, which doesn't happen as we know. There are very few cases where you find single phase solid solution. So something interesting, maybe then people can say the delta H value will significantly vary. Delta H basically seems to be encoding the information about the chemical interactions. But anyway, ever since this particular hypothesis has been seriously challenged, and now people are developing much more sophisticated methods for talking about solid solution stabilization in such kind of alloys. But from 2004 to 2013-14, this was an interesting academic problem, that why few of the elements will go on and form single phase solid solution while others not. I mean, that was an academic problem, but a paper was published. Before I get into that, the idea is that I should say that these high entropy alloys, now this has been applied to range of different material system. You talk about ceramics, you talk about all other kind of materials where these kind of stabilization with the increased number of elements seem to be common. And now that is why some people now call this whole area to be high entropy materials. So as I was going back to something which I was telling, that it was an academic problem before this particular paper, which further increased the interest in these class of material. So a paper was published in 2014 in Science, where they showed that if you take these particular alloy and if you take them, if you carry out their fracture, toughness of these kind of alloys at a liquid nitrogen temperature, they found that as you go to the lower temperature, fracture toughness seem to be increasing, while the strength is also increasing at lower temperature. So this was something very remarkable, because as we know in metallurgy, as what we have been taught, that strength and any kind of toughness or elongation are inversely related to each other, except in grain boundary refinement. So this is something which we are taught in our undergraduate. So what was happening here? They showed that the structure toughness was basically increasing because at the crack tip, nano twinning was taking place, which was bridging the basically the crack, and it was not allowing the crack to grow. So that was something, and a lot of many papers basically came out in this area, basically talking about this kind of phenomenon. They have again published a paper. They have done some work recently last year where they have taken this to liquid helium temperature and shown great fracture toughness there also. So this is not only the structural property. I mean, this particular material, any kind of material success is decided by the idea that whether that particular material can be applied to the challenging situations where other materials may basically struggle, or new applications can be discussed about that particular material. So this is a structural application. Now, another interesting thing is now these materials are also talking about, people are talking about using this concept for developing highly efficient catalyst. So we know palladium is an interesting catalyst, but this is expensive. So they use this concept of generating single phase nanoparticles using different elements such as silver, gold, copper, and platinum with it, and they're able to form single phase nanoparticles there. Interesting part is that you see now, of course, silver is not also very cheaper if you compare with any structural material, but we are talking about catalysts here. So it's certainly cheaper than palladium. So you can hopefully develop these multiple component metal-based catalyst for, in this case, they shown it for carbon dioxide reduction into other chemicals. But this area is again a very interesting and flourishing area of research where a lot of work is being done. So as you can see, structural material, same concept being applied to something else. And more recently, another paper was published. It was on Elinvar effect. These particular high entropy alloy concept is can also be interestingly, I mean, applicable in designing uh, alloys with high Elinvar effect, where the elastic constant of these materials can be kept constant as the temperature is varied in the again, the idea was given that at a low temperature, significant distortion is there in these particular class of material. In high temperature, basically that goes away. So basically, people are engineering the various phenomena associated with high entropy alloys to apply to different interesting class of material. Another interesting application is high hydrogen embrittlement resistance. This is something which where a lot of debate is going on at this moment, that whether these class of material show hydrogen embrittlement resistance property or not. But there are some evidences where they show that these materials show hydrogen embrittlement resistance. So again, this is very interesting in the context of hydrogen economy and sustainability. So this, I mean, as I want to impress upon you guys is that, and these high entropy alloys or materials, they are being applied. I'm just giving you a few examples. They are being applied to n number of challenging applications, and obviously they are being compared with the conventional materials also, which are already available. So and they are exhibiting some interesting properties, and that is why there have been a renewed interest in basically talking about, if you want to design these materials, obviously you have to understand a lot of things. So it's just no more just putting few elements together and seeing something happening, but something more need to be done about it. So moving on, I mean, if you want to design this material, I mean, and there was a very interesting calculation which was done by Drago and was published in Science in their note, which where they calculated the numbers. Suppose you take a palette of 26 metals from the periodic table. So if you take these palette of 26 metals, and suppose you take 5 metals at a time from this palette of 26 metal with the 1% increment, because now you're not only talking about equiatomic compositions, but you're talking about non-equiatomic compositions also, because there can be interesting thing happening in those cases also, because each of them is in a other different kind of a material. So if you take a 5 metals at a time with 1% increment, how many combinations are possible? And they calculated, and they calculated this big number, which is 2.88 trillion combinations are possible. So you're just taking 5 metals at a time from the palette of, uh, and imagine if you have to make these alloys in your lab, whichever method you find interesting, it may be induction melting or whatever you may, or some high throughput method you may think of. But still, a number of 2.88 trillion seems to be large, because uh, I mean, people deal with, say, couple of alloys when they're doing their PhD, and all their lifetime, maybe people work on 50. If one is very, I mean, work in many areas, maybe 10, 15, 20 alloys. But you're talking about 2.88 trillion combinations, and each of them can have an interesting property. So you can imagine the number. Say if you take 6 metals at a time, just to show you, now this number goes to zero 0.9 quadrillion combinations. So you can imagine that there is a very high combinatorial complexity with these materials. So hit and trial approach is not going to work, as I mentioned to you earlier, that it is simply not a feasible approach when you are dealing with these class of material. And not only that, when you talk of these kind of material, you want to come up with a material structure property correlation. And if you are a computational scientist and you're interested to do that, you will be basically relying on some kind of multi-scale model where you will run some ab initio calculation, inform atomistic scale model, and from there take the information at micron scale, and maybe then talk about the macro property of a material. But this is itself, for a single material, is a computationally expensive method. So what can be done about it? So we propose a method which is something called hierarchical multiscale models. So instead of talking about individual methods at the scale, we can discuss the problem in terms of computationally expensive models and computationally cheaper models. And obviously, you can have intermediate precision models. So in the inside, you have a higher precision computationally expensive model, and outside you can have a lower precision computationally cheap models where you can run many calculations. So when we are dealing with these class of material, you have to come up with an innovative method for high throughput screening of the composition for a desired property. Say you want to have high elongation in a particular class of alloys, or you can have high strength, or you can name any property. It doesn't matter. But this approach remains generic to all of these. So you first carry out high throughput, cheaper calculations on, say, millions of combinations, and then you take the interesting elements, and then you carry out in intermediate. If you find some problem, then you can go back, and each of these scales are basically talking to each of these models. It should be able to talk to each other, so that when you find some discrepancy, you can go back and check with the higher precision models in the end. But as you can see, these red dots which are showing over here, some information need to be basically transmitted between these various models, and what should be that kind of information, and that information need to be defined in terms of certain descriptor. So what that descriptor can be, and recently there have been talk about this entropy, and entropy as a descriptor can be used for basically transmitting information between one scale or one model to another. So this is something which I'll basically talk about in detail. So concept of entropy in thermodynamics. Mind it that this entropy I'm talking about may or may not be thermodynamic entropy. So I'll talk about it. First of all, let me talk about the concept of entropy in thermodynamics. So we all know that in our in undergraduate and other places, we have been taught about entropy, and there are a lot of things. Whichever thing which you cannot understand, you basically put in the bracket of entropy. And generally, if I go and ask any undergraduate student or even many other people that what is entropy, the answer we tend to get is entropy is the measure of randomness. It is partially true, but not necessarily true. Entropy does not mean randomness all the time. I can give you a few of the example. I mean, if the entropy is a measure of randomness, then we should not see some kind of orderness which we see around us. Uh, there's a lot of debate in this area how we basically need to represent the entropy. But maybe I can take some questions if some people have in here, because this can be a talk in itself. But you should remember that entropy is not necessarily random. It can be a measure of randomness, but not always. And we can discuss this in detail if someone is interested. So how the entropy was initially defined, we all know this phase. I mean, entropy as a state function is one of the only state function for which we can determine the absolute value. That's why it's very different from other class of state thermodynamic state functions. And we all know that the entropy, as the Boltzmann put out, was can be expressed in terms of the number of microstates or number of possibilities a system can be in, but that is only defined for microcanonical ensemble where NV is constant. So generally we are just given this formula, but we are not given what is behind it. So this is a very rigid formula which provides you with the upper limit of the value of the entropy. So, beyond working on this particular issue, one person made our life very easier was Gibbs, who provided this formula. As you can see, this formula is now defined in terms of some probabilities. And to be more precise, the formula here for the entropy, thermodynamic entropy, or Gibbs entropy, is defined in terms of probabilities. So you basically now are moving from some random particles doing, I mean, behaving in a Brownian motion to something more concrete where you're defining entropy in terms of probability distribution function. So this was a great achievement by Gibbs, which made life very easier for us, for basically at least try to determine the value of entropy. Now, this is something which is defined in thermodynamics. Okay, so if we move forward 50 years, uh, concept of entropy was also being developed in a very different area of, of, of science and engineering, which was in information theory. So a person named Claude Shannon, when he was working, I think in a Bell lab, was working on a problem that he realized you have an information source, uh, where information is generated. You send this information through transmitter on certain transmission line. You have a signal. You receive a signal from the receiver, and you have a destination. A message is received there. So what he realized when he was working on this problem, however hard he was trying, the information which was being from the source and information which was one gets at the destination, there is always some information loss. There is always some information loss. Firstly, he realized maybe the experiments are wrong, but he realized that this is something which is the property of these kind of systems. So if you have a transmitter receiver system, there is always going to be some kind of noise source in the system. There is always going to be there. And he was confused about it, that how to quantify this kind of information loss in these kind of systems. That was the idea Claude Shannon was playing with. And he goes and talked to a great polymath called John von Neumann, and he asked him, "What should I call it? I don't know. I mean, I'm finding these kind of discrepancies in the information which is being generated and information that is being received." So John Neumann made a great statement. He simply says to him, "You should call it entropy." Because in the first place, your uncertainty functions, because there is uncertainty in the information retrieval, has been used in SM, which is statistical mechanics, under the same name. So you can call it entropy, because entropy is basically uh, I mean some kind of loss, and no one really knows what it is. So no one understands the entropy. So you have advantage in the debate. So that's the famous quote which is always being used. And this basically, and Claude Shannon listened to the Neumann, and this basically started the whole area of information theory. And what he did, he talked about some kind of entropy function which where you have a probability of information retrieval, log, probability, and you can see that this have a similar expression as we have seen in the context of Gibbs expression for the entropy. But only difference which you can see over here is that the log has a base of 2. So the log of base of 2 is there because information is transmitted in terms of bits. You can have a value of 0 and 1 and so on. So but with this method, you have something which is defined for the probability distributions with the base of log decided upon the kind of phenomena you are trying to understand. And this is what was something called Shannon or information entropy. So after this, obviously, information entropy have been talked about in a lot of details, and it has been basically generalized to any distribution which is possible. So this is not a thermodynamic entropy. This is I should repeat it over and over again. This is not a thermodynamic entropy. So we are just using this concept, and we will show you. We'll just use this concept to talk about distributions. So we are not talking about thermodynamic entropy yet, but because which is very hard to calculate. So Shannon or information, now people call it Shannon entropy also. So Shannon or information entropy can be defined for distribution also. So suppose you have a system, you can define the probability distribution for any cases. Suppose it can be anything basically. It can be energy of say solute segregation at the grain boundary, or it can be uh, I mean, configurational energy change, any energy, it doesn't matter. It doesn't put any constraint on what should be the energy and how it should be derived. So that is a generated distribution. So you are modeling something and you generate some distribution, say some kind of energy distribution. But maybe you don't know about it, but there is an equilibrium distribution for almost anything. Okay, so there might be an equilibrium distribution for anything. So maybe you don't know about it, what the exact this equilibrium distribution is, but the difference between those two distribution can be written in terms of a parameter which is called Kullback-Leibler divergence. So this is again a very generic concept which is applied to the to any kind of distribution. You can have any, say, two Gaussian distribution. You can write the Kullback-Leibler divergence for that, which is basically information loss. So if you have an inform equilibrium distribution, and if you have a some kind of a generated distribution, you can write this kind of information loss between these two distributions. And as you can see, if this is your generated distribution and this is the equilibrium distribution, you write these kind of expression, which is basically the measure or quantitative measure of the uh, your difference between your generated distribution and the equilibrium distribution. So this is how you can basically talk about information entropy of different in terms of the difference between two distributions. Now suppose I have a I can talk about the relative Shannon entropy. So I can have two candidate distribution, and I want to know which one is the closest to the equilibrium. This is something which I am plotting. So I have a, say, distribution P and distribution Q, and I would like to know which one is closer to the equilibrium distribution. So I can write the KL divergence, so Kullback-Leibler divergence. So I'll call that a KL divergence. So I can write that KL divergence for both of these. I don't know the equilibrium distribution, mind it, but I can write this expression. Okay. Uh, and if I realize that the KL divergence, say, for P is greater than the KL divergence for Q. If this is a scenario I'm talking about, P have a greater divergence in comparison to Q. So we can say that in this context, there is a greater loss of information in P in comparison to Q if EQ is a equilibrium distribution. Now, if this is a scenario, indirectly you can infer that in thermodynamic entropy of Q is going to be higher than P. So indirectly, you are telling, you're not directly calculating the equilibrium distribution, which is hard, which is very difficult. So now you are defining a proxy parameter, which is the relative Shannon entropy. So you generate the distribution for your desired, say, you are interested in talking about two scenarios. Which of these scenario is closer to the equilibrium? This is something which we are talking about. And this provides you an idea about the entropy difference between these two scenarios. So let's apply this. So we talked about high entropy alloys. We have talked about a proxy parameter of such as Shannon entropy. We know that this cobalt, chromium, iron, nickel shows an FeC crystal structure. And when you alloy it with aluminum, if they are all in equiatomic composition, it forms a BCC phase. And if you add titanium to it, it forms the combination of FCC and intermetallic phases. They both have got the almost similar atomic radius, but we know that aluminium is very interesting element. It is a BCC, sorry, FCC element, but it seems to be stabilizing BCC. I mean, in metallurgy, you know, a particular element tries to stabilize its type of crystal structure, but this is very interesting where it seems to be stabilizing BCC. Of course, if you have, say, half aluminium 0.5, cobalt, chromium, iron, nickel, it still shows FCC, and there is a gradual FCC to BCC transition. And in titanium, you just find intermetallics in addition with FCC. So that was a problem we have in hand. Can we use this approach? So we developed this method, which we called genetic algorithm-based atomistic sampling protocol. It has few components to basically derive the configurational entropy. So what it does is that it, first of all, you generate some random structure for a alloy of your interest, say aluminum, cobalt, chromium, iron, nickel. And from there, you take some low energy structures and you use this guess or genetic algorithm based atomistic sampling protocol to generate newer alloys, so parent to children. And once you have done that, you carry out the molecular dynamics. So whatever I'm going to talk about, that is the molecular dynamics using classical interatomic potential. So for those who don't know, you can calculate the energy of the ensemble of atom by quantum modified quantum mechanics, which is very accurate but very expensive. So you can use fitted interatomic potentials also, which can be fitted by machine learning based methods, or earlier people were just fitting it empirically somehow to come up with some rules of interaction between atoms. So it doesn't matter as long as you carry out some finite temperature sampling of a particular configuration to generate the energies, and then you can use simple formulas to generate the probability of occurrence of a particular configuration, and from there, as we have just seen, you can calculate the entropy parameter. Now, whether that is a thermodynamic entropy or not, that is, I mean, generally, I mean, for real thermodynamic entropy, as I told you, it requires the sampling for all the states which are possible, which is generally a computationally expensive proposition. So that is why you have to come up with a smarter method to deal with it. So let me first talk about the gas approach. So what is the aim of this approach? So as I told you, you started with some random configuration, and from those random configuration, you have these alloys, and you want to transmit this information from this to this. So this is parent one, and this is parent two. So there should be a swapping, as it happens in our chromosomes, and the information need to be transmitted. So this is done in this gas approach is as follows. So first of all, we encode the information in such a way that the same type of atoms are arranged in a sequential manner. And we start with randomly finding a position, say any position in the supercell. So this is say I, any number between the and this say this is the I. So I in parent one, this which is this, is correspond to X A Y A Z A, but in the parent two, it will be different because it's a different configuration. Now, what we do, say XB, YB, ZB, we go on and find where that is in the parent one, and this is the J, as you can see over here. Similarly, we go and find the XA, YA, and sorry, this should be ZA, XY, ZA, and this should be K. And with that, you have now when this information is there, you basically swap between the particular atom, and this is how after the swap, this green will move here and red will here, and this blue atom will move here and red here. So by this, we have carried out the sampling for one swap, and with each swap there is an associated mutation. So with that, we basically carried out the configurational entropy for 4 alloys. So as you can see in the context of cobalt, chromium, iron, nickel at room temperature, so you can see FCC has a higher entropy parameter, and it is stable in FCC form. So what we did, we added aluminium, half of the aluminium. Still, FCC remains stable, which is the case. So we are taking, we're just expanding this data to show you that FCC is a stable phase. And similarly, as we are in equiatomic composition, this flips, and now you have a BCC coming out to be stable phase, which is the experimental data which is available. Similarly, for titanium, we found that the FCC seemed to be having the greater entropy parameter. So it can basically predict the room temperature phase stability. So we varied the temperatures, and as you can see, as we vary the temperature, you just look at the FCC versus BCC. So as you can see, the green and the red part, FCC is basically a stable phase throughout the temperature and show the increasing trend. Cobalt, chromium, nickel at the room temperature, FCC is stable, but as we go to the higher temperature, it flips. So it starts to give us prediction that BCC can get stable at high temperatures. Aluminium, cobalt, chromium, nickel shows that BCC is a stable phase, but it shows a decreasing trend. I mean, even though the FCC parameters seem to be increasing, this seem to be keeping more or less constant. And interesting thing is that the cobalt, chromium, iron, nickel, titanium, again, FCC is stable, but its value is very lower in comparison to the other cases which we saw. And we saw that intermetallic can form easily in this particular case. So why, first of all, cobalt, chromium, nickel was a difficult case, that why BCC is stable. And what we found later, that someone, independent group published a paper, and they showed that if you supercool a solid solution of, I mean, liquid of cobalt, chromium, and nickel, indeed BCC can get stable. So there is a BCC stabilization. So we made this prediction in our independent calculation, and later it was experimentally verified by the independent group. Similarly, recently in aluminium, cobalt, chromium, iron, nickel, some paper has came out where they've shown that the BCC can also be stabilized, which we made a predictions earlier with the computational calculations. Now, why this is working out? So when we are running this genetic algorithm, so this is I'm showing you for just one alloy. As we are running these calculations, what we are finding that from this ridge plot, each of this plot is a for one GA cycle, what is the distribution of energies? As you can see, this landscape is changing. So as I'm running my GA cycle, I'm finding lower and lower energy configuration. I'm able to basically, with my gas approach, I'm able to find the low energy configuration faster. And if we do this for candidate crystal structure, the crystal structure which can get to the lower energy faster can have the greater entropy, and hence it can get stable. So that is what we are developing through this particular gas approach. Now I move on to now we have talked about information entropy. Can we apply this to study the order and disorder phase stability? We know in binary alloys that some phases are ordered and some are disordered. So can we basically use this concept and make predictions about it? So what we do, we introduce now in the earlier case, when you have a multiple component system, you just change them and you create the energetic fluctuations. But if you have a binary alloys, it is difficult to create such energy fluctuations because say you have an ordered structure with no vacancy, you just have one energy, right? But if you have a disordered structure, you have a range of vacancies. But if I introduce, if I introduce the vacancy in this system, I generate the fluctuations in energy. And these fluctuations can have the entropy associated with it. Similarly, these fluctuations also lead, I mean, introduction to vacancy lead to the fluctuations in the disordered structure also. I can compare this entropy parameter for ordered and disordered structure, and can it give me some idea about the phase stability between ordered and disordered structure in the binary system. So we start with a cobalt 3 nickel, and it can, as you can see, that cobalt 3 nickel exhibits the ordered structure. So this is at the room temperature. So as you can see, this is just with one vacancy, but 1, 2, and 3 vacancy. As you can see, the entropy parameter is higher for the ordered structure in cobalt 3 nickel. Similar thing we were able to prove for cobalt nickel 3. Both of these cases, L12 kind of ordering is possible. And with this information entropy approach, we were able to predict the order disorder phase stability. Then we got excited and started to apply it to the different cases. Say copper 3 gold, which is again a case. We are able to predict the ordered structure there also. And if we replace gold with nickel, this changes. Now disorder phase is stable. So we are now basically talking about a range of different cases, and we are able to make predictions about the order disorder just looking at the information entropy parameter. And we took it to the other cases also, and we were able to make the predictions at room temperature for iron 3 nickel and iron 3 platinum also. So range of cases we are able to make predictions about the order disorder transition. So this is fine. I mean, this is for binary alloys. Can we do it for high entropy alloys or materials? So there it is difficult because you have a number of components. So what happened traditionally, chemical short range or medium short range or long range are studied in high entropy alloys as you have a composition. You then use molecular dynamics Monte Carlo approach, combined molecular dynamics Monte Carlo approach, and you using Warren-Collie parameter, you predict the chemical short range, medium, or long range order of the system. But that involves you should know the energy of the system. But to know the energy, you need to have the interatomic potential file. But this is not an inverse approach. This is a forward approach. Can we generate the desired configuration without energy calculations in first go? Because you want to develop a high throughput method. And yes, you can. With the Opera approach, which we have recently developed, you are able to generate the chemical short range order in these kind of alloys. So you start with random structure, you can generate short range order, and we have applied this to alloys as well as high entropy oxides. So Opera or order parameter engineering for random system. First of all, we define an order parameter, delta parameter there, where beta is defined for unlike bonds and like bonds in the system. So you have a supercell. So depending upon the number of components, K1 represents the number of unlike bonds in the system. Small n represents the ratio of number of atoms in the supercell, and it is divided by K1, as I mentioned, is number of unlike bonds, and K2 is number of like bonds in the system. With this, we define a delta parameter in the system, and then we started to basically, first of all, we generated a random structure, as I mentioned, which involves B ideal is basically number of bonds system need to have, and B real is the system number of bonds you get in the system when you're just swapping the atoms without any energy calculation. So you can generate the random structures, and then you can basically introduce the chemical short range order once you have got the random structure in the system. So this approach, we have applied this to generate the short range order structure in a medium entropy alloy. Say in this case, chromium bond propensity is increased. This is a like bond, so the delta parameter is positive. So as you can see, if you put chromium together, the energy of the system increases. Similarly, if we took for the refractory high entropy alloys, if you increase the molybdenum tantalum propensity, lambda parameter goes to the negative because that's an unlike bond, and the energy goes to the negative. We have applied this to study chemical shortening order in high entropy oxides also. As you can see, if you keep these are all constant composition cases, the energy doesn't show any trend. We're not comparing it per se, we're just I mean, in this particular case, we're just increasing the copper cation propensity in this entropy stabilized oxide, and we were able to come up with a prediction that basically if you increase the copper propensity, you increase the energy of the system, which we have earlier predicted. So it can be applied to any range of any kind of high entropy material. Now, this is about the can we use it to now make the predictions about the property. So strength is obviously the interesting parameter where we can talk about. So we know that solid solution strengthening take place in high entropy or medium entropy alloys. So there obviously the Warwin gave the initial model where they talked about how the dislocation changes in I mean, the topology of dislocation changes that it traverses through the disordered landscape. So what we said that, okay, we developed a simpler model where we say generate the random configuration, introduce the edge dislocation into it. Why edge dislocation? Because we are talking about the strengthening due to the volume misfit, and we calculate the dislocation misfit interaction with the pressure volume term, and then we did it for some configuration and then carried out the Monte Carlo on top of it. So what is happening that if you see this number, that if you for the same number of configuration, you get some kind of a distribution of energies. Okay, so now we are talking about the energetic terms, and these distribution of energies, the full width half maximum of these distribution have a linear correlation with the entropy parameter which we just talked about. So can these entropy parameter can make some prediction about the strength, and we compared this with some experimental results, and as you can see that it shows some correlation with the critical resolve shear stress. Obviously, strength is a complicated parameter to predict, and we're talking about a Cantor alloy with some complicated elements such as manganese. As you can see that for most of the cases we're getting some linear correlation, but particularly element having manganese seem to be not coming in the line, and this is visible here also in this context. When we take out the manganese, rejection fraction shows a clear trend. So delta V values seem to be very important when we want to calculate the volume misfit. So some kind of magneto-volume fluctuations are taking place. So we carried out the large-scale density functional calculation with the impurity in matrix approach. So you have a matrix and you put another element there. So cobalt, chromium, iron, manganese, nickel, all these elements we can take, and just instead of just doing the full alloy in one go, we started with some impurity there. I mean, say as you can see over here, say cobalt, chromium, iron, manganese, nickel in FCC form and in their ground state structure, and adding other element as an impurity. One thing which was very clear that cobalt nickel shows very negligible distortion. I mean, atomic scale distortion, but chromium is the one which in FCC form showed significant distortion. And another interesting case was the manganese. Manganese was showing range of different distortions. Some case it was showing distortion, in some case it was not. So we carried out better charge and volume analysis on FCC chromium matrix, and what we found that uh, the volume of the impurity atom in the center when it's surrounded by chromium shows some kind of volume collapse when the ground state is antiferromagnetic. Okay, because chromium with other element, the real structure is antiferromagnetic in nature. So if when we force the ferromagnetic ground state on these elements, we found that this kind of I mean, volume change or volume change was gradually reduced. And initial hypothesis was that this distortion is basically coming from the fact that the impurity atom volume is basically reducing somehow due to some magnetic effect. And that is what is leading to the distortion in these kind of systems. So we study this that why that might be happening, and as you can see over here in context of the FCC cobalt nickel, where we don't see any distortion, that if you scan through one end to another between this is an impurity atom and this is a matrix atom, what you find is not a very significant magnetic moment fluctuation there. But in context of chromium matrix with the cobalt impurity, as you can see, there is a fluctuation in the magnetic moment. So magnetic moment is significantly changing as you're moving from one end to another. So this was very interesting. So spin fluctuation is taking place, which might be leading to some kind of a magnetovolume contraction for the because when we carried out the ferromagnetic case where we constrained it, which is not a ground state of the system, you can see that these fluctuation basically disappears. So what happens with the manganese, which was where this is happening? So in some cases, when we find high magnetic moment, we are finding significant distortion, while in low magnetic moment, we are finding limited distortion. So what is happening here also? So we studied the spin fluctuation here also, and we found that this is what is happening. I mean, in a case where you have a high magnetic moment and with a high distortion, the fluctuation in the magnetic moment is taking place. So we scanned it in a real space and we found those fluctuations. And in the case where there is a limited distortion, these fluctuations are not there. So the spin fluctuations play a very crucial role in developing distortion. And this should be accounted for when one wants to calculate the volume change associated with an atom in high entropy alloys. Because this is just impurity in matrix. And these calculations are complicated. And you talk about high entropy alloys, this will be further difficult calculation. So this is what I have talked about. I've talked about the crystal structure predictions can be carried out with many body potentials. You can use pair potentials also. We have to check. This can be used to entropy parameters can be used to predict the order disorder. Can it predict the transition temperature? That is a question. Uh, this can be, I mean, generally it can predict some kind of equilibrium phenomena, but what about non-equilibrium phenomena? So indirectly, we're talking about dislocation, not exactly glide, but the strength prediction. So maybe it can. Uh, Two codes which I have talked about, one gas, another Opera. Both of these codes are available at my GitHub repository for anyone for free to use. So you can go ahead and if you want to design some high entropy alloys, you can use this code for free and develop your own codes on top of it, as long as you acknowledge the code you have used. So yeah, I mean, now I should acknowledge. So whatever work I have been presenting is not done in isolation. I have worked with many people. Of course, Colin, Freeman, and Shepard and Russell initially, and now talking to Sornovo and Marcus in Oak Ridge. Students in my group, Dhiman and Shubhadeep, started to work on this order disorder transition earlier. Now in my group members, Suman, Kaushik, they are working on this issue. Rahul, this MTech on information entropy approach. And obviously computational facility by CDAC and OLCF is also acknowledged. And I think this is from my side, and I'm happy to take any question you might be having. Over to you.
Yeah. Thank you, Dr. Anand, for your insight talk on the entropy-based material. So it's really very informative, and it's a large chunks of experiment, or say you can say data you are showing. So it will help to all students. So now I requesting students. So if anyone have any question, any doubt, so Professor Anand is here, so he can help you out. Question, guys. Please raise your hand if you have any question. Then we can unmute you, and then we can ask question. Okay, I think no one have no question. So now so Dr. Anand, so thank you very much for accepting my invitation for this talk. So definitely we'll means in the next time also I will contact you for your for your means to spend some time with us. So thank you very much.
Thank you. Thank you. It was my pleasure. Thank you.
So our next talk will be start from 11:30. So we have enough time for a small break. So the students, so please come in time. We will start sharply at 11:30. And our next talk will be from, I can share the screen. Okay, then just give me a minute. Yeah, our next talk will start from 11:30, and our next speaker is Dr. Itishri Mohanty from Tata Steel. Okay, so let's take a small break, and we'll meet again at 11:30 sharp.